everyone. Can everyone hear me all right? Great, awesome. Well, thanks for coming to Near Real-Time Analytics with Apache Spark. Scheduled to speak was supposed to be Brandon Hamric and myself, Beck Cronin-Dixon. Unfortunately, Brandon Hamric couldn't be here today due to a family emergency, but I want to acknowledge that a lot of these concepts and a lot of this planning was due to him, so accolades where they're due. I am a data engineer at Overwrite, often working to scale our ever-increasing ingestion needs. So what I'm going to cover in this talk today are the components of near real-time data, what you need to know about your data before you ever pick an ingestion approach, and also what you need to think about in terms of scalability for the future of that data ingestion. The requirements required for use case per your data ingestion, so depending on which source of data you want to ingest, what is it going to be used for, and what will that take? And then we're going to get into the meat of things, which is the data ingestion approaches. I'm going to start off with a lot of traditional batch approaches and then move towards more of a streaming approach, just to show that you don't have to jump straight into a streaming approach because it does require a lot of resources and you can incrementally move there. Next, we're going to look at each approach side by side to look at the read and write benchmarks so we can see what it'll do for your write and then your read. And then I'm going to close with the considerations of the components and requirements we've covered at the beginning of the talk. So components of near real-time data. First, you've got to look at the size of your real-time data that you're looking to ingest. This will determine how optimized you can get your latency. So if it's terabytes of data, depending on the approach, you may only be able to get hours or minutes. You can't reach seconds, even if you're doing an incremental approach of taking changed rows. It could just be too much data. Then you've also got to look at, if you're doing the incremental approach, how much data do you already have in your data lake? Because you actually have to overwrite most of the time if you're not doing an append approach. So that will go into your latency as well. Next up is mutability. Is your source data mutable or is it immutable? If it's immutable, you could take an append-only approach, and then you only have to think about compaction. Otherwise, if it's mutable, you then have to think of deduplication and other things like that. Next is your schema evolution. How often does the schema of your real-time database change? If it's often, you'll have to think about using either a file format that can support that, or being able to catch those changes early on and have your ingestion approach either drop the table and then do a complete backfill, or however else you want to deal with that. This could lead to even more latency. Next up is deduplication. If you have changed rows in your source tables, then you're going to have to either do the deduplication on the right side of the ingestion, or when people read that data, either side is going to cause some latency. You have to decide where you want to do that and in what approach. The next thing is your infrastructure. What are you actually, when you ingest your data, what are you actually using it for? Is it only for ad hoc queries? Is it to run batch processes or streaming queries? Or is it all three? Because you need to think about this. Next is storage. Once you have read your real-time data into your data infrastructure, how are you going to store that for read optimization and also for further pulling that down to merge with data that's coming in? I'd suggest if it's a large amount of data and it makes sense to partition it, definitely in a way that a lot of your read is going to use that column to filter that data. Then once you have your partitioning, you've got to think about the files within your partition, the size of those files, and then also how you're going to order that data so when you pull it down, you don't have a complete shuffle every time. Next is your file format. So we've touched on that a little bit. So if you use a file format that deals with schema evolution, if that's not a problem for you, you might want one that's optimized for read or serialization and deserialization. Next, and this leads us to compression. There's two things to think about with compression. The first is in your source database, so your real-time database, how is it compressed and how are you going to deal with getting that through using Spark? Then once it's deserialized, how are you going to compress that again, using Snappy, or what is going to be best for your approach for reading? Next up, we're going to talk about the common requirements for data ingestion. So each one is different. You can't think about ingesting from different sources to be the same. This is because you'll have different latency cases. Now, most stakeholders, if you ask them, how quick do you want the data? I want it in minutes, I want it in seconds. That's probably not what they need. You need to understand what their use case is. What do they need it for? If it's just to send emails out on a daily rate, you probably just want to ingest it just before that they do that. That way you get the most recent data, but you're not wasting resources pulling every hour. This comes to understanding your upstream and downstream dependencies for that data ingestion. If your upstream dependency, if it doesn't actually get updated all that often, do you want to have those resources, that high availability up, trying to pull that data that doesn't actually bring many rows? Especially if your downstreams, the reason that you're pulling that data in is only for a process that's going to run daily, weekly, when. The next thing you've got to think about is some implementations fit to certain latencies better than others. So depending on the approach you choose for ingestion, if you're trying to do a full overwrite and you expect minutes, that's not going to happen. So depending on your use case, that's going to determine what approach that you can use and you can't use. And then also, you can have a mixed grain approach to ingestion. You don't have to choose one for your data infrastructure. And also, you can use the same tools to build upon getting better latency. You can use the same tools. And you can use Spark for a lot of this. So I'm going to go into a little specifics about our requirements of Overwrite for data ingestion. We have very different real-time databases. Some of them are web interaction data, so that's billions of records per month. We take more of a streaming approach to this because people, especially people are expecting that data quicker even for ad hoc querying, and we also look at site health through that. We have our transactional database is mysql, and that is multiple terabytes. There's no way we can do full overwrites of every table in there. But also for streaming, sometimes some of those tables are just too much to have a streaming approach on top on by itself as well. And we're going to get into how we can actually support larger tables with a streaming approach, but using batch ingestion in the background. We have external and internal reporting requirements. So this helps us determine what tables are needed at a streaming approach versus those that we can wait a little bit to do a higher latency ingestion with because it won't take as much resources. We also have set our ingestion up in a way that if suddenly a table becomes needed for a lower latency ingestion, it's easy for us to pull that, to swap that out. We take a mixed grain approach, so some real-time data we ingest seconds and some daily. As I said before, it just depends on the use case. And we don't rely on our stakeholders to understand what they actually need. We work with them and we try to understand what they're actually using that data for and what their end goal is. So it's very important for data engineers, I think, to understand that the business use case for ingestion as well. And so the stack we use is Spark for a lot of ingestion. We use Presto for our ad hoc querying. And then we use, for storage, we use S3 and HDFS depending on how available we need that data and also if we're going to do broadcast joins. And then we use Kafka for our messaging queues and for a lot of our streaming topics. We use Parquet for our file formats as that gives us a lot of read optimization for scans and we have a lot of ad hoc querying going on over the top of our data that needs a lot of aggregations. So now we're going to move into the meat of this talk. And when you're looking at this, you'll see a lot, you're probably thinking, where is all the streaming options? They've been covered extensively. I want to try and show you what's under the hood of a lot of the streaming options and how you can roll your own until you need to move to a really solid streaming solution. So we're going to cover full overwrite, batch incremental merge, append-only, key value store, and then this hybrid batch stream view, which Brandon actually came up with to use incremental merge, and then also to fill that gap of latency to have your data available. We'll read directly from the database, and we'll go into that soon. So the first approach is full override. This one's pretty self-explanatory. You take all the rows from your real-time database and just overwrite your path within your data lake. There's nothing fancy about this. It's a direct ETL. It's the traditional approach. It's really simple to implement. There's not much going on, and your queries are very, very fast and simple because you have complete control of partitioning, and you also have no logic going on in the reads. Now, the bad side of things is that it is a significant load on your real-time database, and your ops will probably be very angry at you if you do this at a very frequent pace. And so it also means that there's high latency because the time it takes to ingest all those rows of data and then to also write that up to your whatever story, especially if you're transferring all those rows through the network. That also means a really high rate on input-output requirements, especially if you're using a lot of connections to pull your real-time data in. So we're going to look at a code example for this. We're using Spark's jdbc data frame reader to connect to our real-time database. Now you see one important thing is the partitions we're setting. We're setting a lot of partitions here because we're pulling a lot of data out. And it all depends on the size of your table. But the way that the partitions works is it's only ever going to open up as many connections to the real-time database as you have executors. But this will set up 240 queries against your real-time database to be executed by those connections. So we're partitioning by ID, so we can set up our where clause for those partitions. So if you see our lower and upper bounds, we're actually taking, for this example, we're taking the lowest ID we can find, the largest we can find in MySQL. So we're pulling it all in. We're just taking that data and we're just writing it to our path in our data lake. So the next approach we're going to touch on is batch incremental merge. This is extending from the example we've just seen, which is we've already ran our full overwrite, or any way we get our data into our data lake, and then for any new or changed rows, we pull them in. Now what we have to do is we have to pull the existing rows from our data lake, the new rows and changed rows that we've taken from our real-time data. We have to union them. We have to deal with deduplication, and then we overwrite that entire table. The great thing about this, compared to the last approach, is that you have a lower load on your real-time database. So ops will be happy about that. And like we saw before, the queries are fast and simple because there's no logic as well. It's exactly the same write to your storage as we saw with full overwrite. Now it's still relatively high latency because you have to write all that data back to your storage. There's no way around that for this. So obviously you have a higher I/O requirement like the previous approach, and you need to make sure that you have reliable incremental fields so you can know what data to pull in from your real-time database. Otherwise, if you don't have that, you're going to have the best case scenario is you're just pulling rows you've already seen. Worst case scenario is you're going to be missing out on rows, so there'll be a discrepancy between your real-time database and what you see in your data lake. So this example, what's going on is we're taking our base events DF, everything that's in our data lake that we already have for this table. We're using the jdbc reader again. This all looks pretty familiar, except that we're having less partitions because we're pulling less data out. We want to reduce that load on our real-time database, and we don't need as many partitions because Spark doesn't need to have those bottlenecks. So we're also changing the partition column we're using. Changed is often is what any transaction database should have. So we're taking all the columns we've seen that have, and we're reading the max change from base. That's our lower bound. So the last row that we see in our database, that will be our lower bound, and then our upper bound will be, we're pulling from the real-time database itself. So we now have that filter that we can apply. And a difference to note here is also the filter. The JDBC allows pretty good push downs, and you might be wondering, why do we have that? Because we already have the lower and upper bounds. For some reason, if you don't include that, what it will do is it'll it'll have a where, one of the SQL queries will be a where clause of everything below your lower bound. So it'll actually pull everything in still, and you'll have a huge bottleneck, and you'll run out of memory and you'll wonder what's happening. That's what it is. So once we have those new rows, we then merge the base rows and the new rows together. We have to do something about deduplication. You don't have to do it here. You could do it in your read, but that would be very messy. You also don't have to do it this way. There's a lot of other optimized ways to do it. This is just a really explicit approach to show. And the reason you're ordering by is because drop duplicates actually just takes the first one it sees. And then you're taking that new updated DF and you're writing it back to the same path. So the next approach we're going to talk about is append-only tables. This is great for if your source data is immutable. What you're doing here is you're querying your real-time database for any new or changed rows, like what we saw before in incremental batch merge. And then what you want to do, instead of just writing those all up as it is, you want to coalesce so you don't have as many files. This will cause problems within your reads. And so coalesce to a number that makes sense for your data size. You'll also want to compact hourly, especially if you're doing this in minutes. You'll have a lot of part files, and so a compaction hourly will just optimize those reads even more. So the great thing is this is latency in minutes because you're not doing that full override. You don't have to pull down what you see in your base, what you already have in your data lake, and then push it all back up. You're just appending a part file to either your petitions or your base path. It's really simple to implement, as we'll see in a second, and then it really simplifies your data lake because you don't have a lot of that complex logic that you've got to monitor, such as deduplication or anything like that. The compaction is the only part that's really a little bit complex. And as I said before, it's great for immutable source tables because you don't have to have you don't have to do you don't have to do anything special for them. Now, it does, as I said before, it requires a compaction process, which is just even further coalescing files that already exist in there on a frequent basis. This, depending how you do it, that can use a lot of resources. It can actually cause your table to be unavailable. You could put a temp view over the top of it in the meantime, but it's still some logic. Every time you had to add a step like this, it's more logic just to monitor. So this is the code example for append-only. As you see here, as before, we're just taking the base event. I've shown the base events here just to show that we write to the same path. And so we're just taking new and changed rows, same partitioning logic and the filter for the predicate pushdown. And the one thing that we've added is the coalesce. And so, as I said before, the number that you coalesce your files to will depend on your data size. So make sure you do a lot of testing, experimenting beforehand. And then all you're doing is you're using the append mode for Spark, and then you just push it up to the same path. The next approach is key value store. This one's pretty easy to understand. You're just pulling the rows that you need from your real-time database, and you're upserting them to a key value store. Pretty simple, right? The great thing is it's straightforward to implement, and Spark supports a lot of file formats for key value stores, and you can also just roll your own if you need to. It's built in potency, means that any time that you, if you need to do data recovery or you need to run it again, it'll do the exact same thing. And it's a great bridge between your data lake and web services. You don't have to build anything in the middle if you need to get data back into the product. People can access the data within the key value store. All right, the bad. Batch writes to key value store, they can be slower than HDFS. That's just how key value stores work. And it depends on your key value store. We use Cassandra. We ran into some write and read queries, some high loads there. But if you use something like Accumulo, HBase, or even if you set Cassandra up right, because we just did that for this presentation, so we weren't really worried about getting a lot of high optimization. And key value stores are just notorious for being not good with the large scans. So if you're looking for something to store things where people are just going to get things from a row-by-row basis, a key value store is perfect. So the logic here, we've got the same logic for getting new rows from MySQL that we've seen before. And then if we move down to how we write those to Cassandra, you can see the file format. Spark has a lot of those. And then you're just appending it because it will, even if you have if you have deduplication, it'll just overwrite. It's how key value store works. And you just for your options, depending on the file format and what key value store you're using, you'll need to understand how to set that up. So this is the next approach. This is using incremental batch merge that we saw. But we saw that that actually still had a little bit of latency involved because you have to you have to merge the new rows and change rows you pull from your your real-time database, and then you've got to get everything from your data lake and then overwrite that path. Well, what about how do you solve that latency? Well, with this approach, we do that by using the hybrid batch stream view. And that is just pulling directly from your database and putting that into a temp view. And you're not pulling everything, you're still using what's in your data lake. And then you just lock the tables, and then you can just switch them out for when the incremental merge is done. So this gives you data within seconds. It depends how you set it up. There is a little bit of a complexity involved. It depends on the amount of data you have as well. It's pretty easy to set up as well for the batch job, as we saw incremental merge. Although the streaming part of things, the logic that we have to close that latency gap for this approach, that can get quite complex. And the great thing is Spark can do both of these jobs. So we're not using two different tools, or we're not having the logic in two different places. There is a lot of processing that's required on read because you do have to do your deduplication there as well. So this is an example of the hybrid batch stream view. You're pulling your base event, you're pulling what you already have in your data lake. Then you're getting all your new and changed rows from MySQL. This is exactly what we've seen before. And then what we're doing, this is an example of what we do for the stream approach. We already saw the batch incremental merge, so that would be running in the background. This is how you bridge that latency gap. What you do is you union and you deduplicate, as we saw in other examples, and then you're just going to create a temp view. And now people they can now query using this instead of what's happening, the path that's happening in your incremental batch merge. Once that finishes, you can then unlock it and switch paths using your metastore. And so you might be thinking, doesn't data lakes just do that? Delta lakes just do that? That helps simplify it a lot. It helps do the incremental batch merge. That's what's great. And it's open source now, so that's fantastic. And the big reason why a lot of people did incremental batch merge is because of ACID transactions weren't really great in Spark, especially in using org file format. Had a certain way to do it, but it still lacked a lot of the transactions needed. Now Delta Lake really solves that, so that's fantastic. I can't wait to play around with it. And then the reason why you would want this stream approach on top is because you want this frequent ingestion process to keep updating what you have in your data lake. But you want to avoid a lot of latency involved with that, because there's no way around having to rewrite that data up. Or if you're doing Append-Only, getting out of doing a compaction process, which can take your data offline for a little bit, or dealing with deduplication in your reads. So the hybrid approach still bridges the latency gap with a Delta Lake for the moment. So now I'm going to look at some of the benchmarks of these approaches together. If you can see, the full overwrite and batch incremental, as I mentioned before, is really high latency. So this approach, it's very simple though, and it's less resource intensive. So you'd want to do something like this if you have, especially a full overwrite, if you have your data size from your real-time database is not much. Say that data gets overridden every day or something like that. Because the read time is very, very simple. It's very, very small. It doesn't take anything at all because there's no logic that you have to do, so the deduplication we saw or anything like that. Batch incremental merge is less. It has less of a latency for the write time because you're not taking everything from the database, so that's a lot better. And then also, if you see the hybrid batch view, which is implementing batch incremental merge, it has very, very low latency because it's having the streaming approach on top. Append-Only has a high scan because you have to deal with deduplication there. And the key value, our key value store had a very high scan because key value stores are notorious for that unless you really optimize for that. You know, there's some, like Cassandra has a way to set an index, but you really have to optimize for that, and we didn't. So don't take that as with a grain of salt. You need to look into each different key value store. So you might be wondering, like, where is Spark streaming in this talk? Why is this on the Spark streaming? Why is this on the streaming track? The problem is that if you have a lot of data that you're streaming in all at once and you want to join them a lot, you can have some very bad performance on top of that. A lot of high CPU and I/O input. It's just you want to avoid if you can get away with it. If you can have a lower grain, you want to have a lot more of your data ingested through batch. So understand your use case there, and if you can get away with doing some of these other ingestions, because they're still near real-time data. So save your stream approach for things that really need to have like low latency. And then, yeah, you're decreasing your batch intervals, so that gives us more stream to batch joins. As I said, like that's what you want, especially if you're having aggregations over a certain table a lot of times. All right, so I've got quite a bit of minutes. I talk really fast, so I apologize. But I'm going to talk a little bit about these considerations. So understand your use case. I know I've been harping on about this through the talk, but I think a lot of people, you have stakeholders, something from the product side, say, we need to ingest this data, it's new, get it in. You're like, yes, okay. And they're like, we need it within minutes. And we kind of just take the word for that. But that also comes with a cost for, it's a cost of resources, of of financial resources, of human resources, and also of our infrastructure. Oftentimes, a lot of us in our jobs, we can't just say, hey, I need this new tool, it's going to cost X, and people are going to give that to us. We have to sometimes deal with the tools that we have in the infrastructure we have, with the intention of then moving, eventually moving to a lower latency. I'm a firm believer in an iterative approach to say to people, hey, I can get you this right now. This will give you it. Otherwise, you have to wait for this many weeks to get this part. And often people will be like, oh, actually, no, I'll take this approach over here. It's lower, it's a higher latency, but it's actually what I need anyway. And then so with the use case, that will determine your latency needs, which will help with the approach you choose. Because maybe they really do need seconds, therefore you take something like a structured streaming approach, or something like we saw with the hybrid batch stream approach. That a lot of time will come with experimentation as well, and eventually you'll get to a point where you'll have all these different approaches to ingestion in your infrastructure, and you'll know, hey, this one will get me minutes, this one will get me hours, how big is my data size, and you'll just be able to quickly be able to know the requirements, the considerations for your real-time data, and then you'll be able to properly tell stakeholders, this is what you really, this is what you really need, or we can't do this because of this, or will be a better approach. And then you also have to deal with, in that is deduplication. This puts more latency as well. So the more deduplication you have, you've got to think about that's more time. And where are you going to do that? Is that going to be on the read or the write side? If you take an append-only approach, you're going to have to do that for every single read, really. Or you do that you create a temp table that frequently updates every time you pull in the new part files. So that's very important to understand as well. And then storage, where are you going to store your data? I think that's very important, because if you're going to store it in something like S3, so you're pushing it through the network, that's more time on latency. And also we've got to talk, you've got to understand compression and how you're going to save that. Is it going to be using Snappy, and then what file format, Parquet? That you also understand that for latency needs, but there's understanding what the latency is on the read time, and there's understanding the latency on the write time. So on the write time, if you can get that to the lowest latency, that's great. But if you've taken shortcuts to get that latency, and now that you now have that latency on the read time, that's going to affect you. So you've got to understand. You've got to try and weigh those trade-offs. So this is just a sample of the JDBC reader we use. I thought it might be helpful for people. We had to play around with a whole lot of the different settings. And I think I sped through that, so I've got minutes if anybody's got any questions.
Yeah, it's kind of interesting to show all the metrics and taking a practical approach to solving the problem between what is really needed at the end of the day. Oh. Yeah, if anybody have any questions for Beck, yeah, please come forward.
Hi, I was sort of wondering, your JDBC reader showed that you're actually directly going to the MySQL database, yep. But then there was other options where you were analyzing the transaction logs and not the table itself.
Which one? Sorry, I'm going to put that back up.
So for all the import options, were you directly going to the MySQL database for?
Yeah, we were directly going to the MySQL database, and that's where you could actually, for a lot of these approaches, let me go pull one back. For a lot of these approaches, you could put streaming in there and do a lot of this logic for anything you need. So a lot of streaming approaches roll their own deduplication and the things that we're doing. But you could use a really simple structured streaming, or pulling from Kafka logs or bin logs using Maxwell if using MySQL, anything like that. So it's just replacing the JDBC. The JDBC, if you set it up correctly, it's really fast. It's just that a lot of people don't it took us quite a while to find the right configurations. And I know that a lot of, what I've read online is a lot of people it's too slow, or it doesn't work. It does, they've set it up in a way that you really have to know your data, and you really have to know what you're trying to get out of it.
But, so I guess my question was mainly regarding, there's no way to balance out the load that this job would affect the actual production system that you're running. Even if you're running clusters with masters and slaves, that they would have to deal with the requests that are coming in from the backend job. So I was wondering if you've considered something like Scoop to analyze the MySQL transactions to import it into HDFS.
We use Scoop at Eventbrite. We're trying to replace it because it has its own problems, especially around schema evolution. It really doesn't handle well with that. For certain schema evolution it does, others it doesn't. And we've just found for certain size tables, this approach works better because you're not, especially, you have to read from a replica, and it has to be a replica that doesn't have a high load on it already. So if you can work out with your ops to get that, this is a really good approach. If you can't, then something like Scoop is great. You still have those concerns. But yeah, you have to be careful when you use something like this about your high load on your real-time database, for sure.
Any other questions? All right, thank you, everyone. And we would also appreciate it if you could rate the session in the app. Thank you.